Passive cooling at its best. Homebrew passive cooling. No motors involved. Anyway, the fan is more important to us first, and we're going to use the same stator. But for the generator, I took something I saw on the internet. A fellow, I can't remember his name, or I'd credit him. He's trying to explain this molar-free engine generator that's supposed to create more power than was put in to initially turn it. It's supposed to pick up speed over a couple of days and generate electricity. Obviously, there's no free ride. The meter's ranging in voltage, and the resistance is the resistance of the meter, which is designed to be extremely low. It's a meter. If it had a lot of resistance, it would change the output on the scale. You'd be using up power in your meter. So anyway, the way he explained it, he had 2 sheets of paper, and he had holes in the paper that you could see the magnets on the bottom thing. And when you turn the top or the bottom piece of paper, the magnets come past the holes, and the coils were drawn around the holes. And so I did a change on that. First, for just a single phase, I made a sheet that covers up 2/3 of the holes, basically. And I looked to see which magnets were trying to slow down the motor and which were trying to pull it faster. And I put an arrow out external to this ring of drawn coils, pointing the direction that it was trying to turn the rotor. So out of 37 magnets, there was like 19 of them 19 or 20, something like that, trying to make it turn, and the rest of them were to 1 degree or another holding it back. And the total amount they held it back was about the equivalent of 4 of the stator coils. I said, well, that's crap. And I was looking at it, so I've only got 2 extra magnets, and it works perfect for the first 180 degrees. So I said, well, if the second 180 worked like the first, they'd all be pulling the same direction. So I stutter stepped the 0 coils to 2 of the same, counterclockwise, and 2 of the ones 180 clockwise. And all of them pulled, and all of them working, all going the same direction, everybody happy. So then I put on another set of holes, a different mask, over the thing. And because these stators, you go in one set of coils, then they're connected to the other set of coils, you go out through that set of coils. So in my 30 coil stator, 20 of them are in play, 10 of them are not connected. And every time the magnet goes from positive to negative, it drops one of those sets out and adds the one that was off. And then the next step, it'll drop off the other one that it started with and pick the one that turned off first. And that's how it goes round and around. It's turning on 2 phases and turning 1 phase off. The thing worked with 2 phases drawn that way because the coils were done clockwise and counterclockwise alternately, and the magnets were alternating north and south. The 2 phases work just like 1 phase. They all working for me. And then I took an arrow and drew it straight away from the thing, which means it was not doing anything. And that was the color of the coils that weren't turned on. So I did that for all 3 combinations of coils that had a phase turned off. And all 3 phases were working for me. And I got to thinking, if I'm doing a generator and I'm taking out 10 coils, 10 coils, and 10 coils, I think the phase goes to a 3-phase rectifier to make it into DC. They're all working for me. There's nothing making negative voltage in a ring that's making not positive voltage, canceling it out. So that's why we think that this is going to work on the generator and the motor. And being a cautious, pessimistic kind of person, always seeing the downside of everything, I cut the stator in two, right across the middle. All the wire connections is at one side of the cut on one end. The other end, the initial idea was just to cut the three wires that were connecting all the ones that were in series for each phase. I cut a wire that was going from one red to another red and one from a blue to a blue, and put brass screws up and loop ends on a piece of regular old copper stranded wire, connected them back together. Now what this lets me do is flip that piece upside down. And so if I'm stutter stepping where I've doubled the two clockwise together on one end and two counterclockwise on the other end, if I flip it over, it's back to this alternating clockwise and counterclockwise all the way around. No loss. Second thing for this is I've got a 32 magnets times 2. There's 2 rotor plates. That's 64 magnets. They can pick up around 200 pounds apiece. And I figured maybe as much as, also, if I was using wasn't using the N52, if I was using N42s or something like that, I'd still have 110 pound off of one magnet, when they touch. But as you move them apart, the attraction goes down. As you move it away from the magnetic field, or a magnet on the other side, same thing. But the fact that I've got 2 of them working opposite each other, and then they're alternating on the rotors, I can see a quick 11,500 pounds trying to suck them things together. You don't want to be handling something like that. I forget what I was working on one time. I used to work industrial maintenance. Oh, I know what it was. It was an electromagnet. It was a magnet. Went down there to, I was working in the engineering department of a steel mill, and they were ordering new magnets for an aisle that mixes scrap to go in the steel furnace. And I went down there, and they had a 2-inch plate on the floor, and they were throwing sandwich scraps and flipping the switch anytime a rat ran in there to get the scraps. And that's how they spent their break time and lunch, was crushing rats with electromagnet. It was a big zoing sound, and then the plate would fall off. And I said, you want me to buy you new magnets because you're destroying them? Not happening. I have to buy the magnets, but I don't have to have you guys working here. And we can do something about that. So you're going to stop that today. I know it's kind of hard to stop having fun, but let's stop doing that. And I was back down there a couple weeks later for a whole new control system for a crane cab, 1,430 ton capacity crane. Cab tore all 2 pieces. I says, how'd that happen? Well, the cab goes up and down with the load. There's 27 levers in this cab because it runs its own crane and it runs a drone crane that is electrically separated. It senses distance with just radar emitters. So they can't touch unless you do something really stupid, like turn one going down north and bring the other one back up from the south, and you have them buried, the power buried. Well, it can't decelerate that. There's going to be a bunch of dirt falling from the ceiling. Anyway, this guy was a relief operator, and he got a little confused, and he's got like 3 bridges on his crane at different heights, and one of them's got about a 5-foot diameter magnet, and one's got about a 10-foot diameter magnet. They got auxiliary hoists on them. And then the top one has got just a giant winch that can pull up around 430 tons, I think. Got miles of cable and things, but they changed that cable, it's an all-day job. They have to wind it down and connect the other cable to it and then pull it back up with its own motor. But this guy had a 12-foot or 10-foot diameter magnet he accidentally powered it on full power. And while he got busy doing stuff with his main hoist, it was scrap, so he was allowed to take his cab down to the level that he was working at. Because the cab goes up and down, telescopes up and down. He's got his own water fountain, bathroom, whatever in the thing, but he can only get on and off of it at 2 different catwalks. Anything in between that, there's no catwalk. So he goes down to see what he's doing and where he's setting this thing down. And he grabbed the wrong lever and he run a 150-ton capacity hoist with magnets on it to the cab. And when it got about 10 feet away, it sort of turned on edge. It was like somebody throwing a pie in your face. Ka-wham! Knocked the cab right off altogether. So it was stuck to the magnet. And with this new generation of cranes, the controls, the starters, and all the contactors are not in the cab. They're on the crane in a NEMA 4 enclosure. Because before we had open contacts on some of the mills still had them. Every time a contact opens or closes, it's like a welding flash inside the cab. So these guys get terrible eye strain. They'd be wearing sunglasses. They'd have canvas hung up in front of the contactors to try to reduce the amount of flash. Of course, the sparks from the flash would set that on fire. Anyway, this guy had knocked his cab off, and he needed all the electronics that goes up to the stuff upstairs. And somehow the magnet stayed stuck to the cab, so he was just swinging back and forth about 50 feet off the ground. And they called riggers to come over and got him down. Anyway, having seen a control cab ripped off a crane a while back, I can envision what would happen with an 11,000-pound force when 2 magnets came together if you were somehow between that. So the 2-piece stator lets me slide each half in from either side. It lets me have half my coils from a phase wired together, the other half wired separately. I can change the polarity of the alternate coils from clockwise to counterclockwise by the jumper wire where they all come. Jumper outputs are still going to be wire delta connected. So that's what we're doing on the stator. The stator is, that's the heart of the damn thing. Then you have, the second most important thing is an inverter that takes the power out of the batteries or whatever you're storing it in and turns it into the voltage and a single phase or DC, whichever you want. Usually single phase 110, single phase 220, or split system with both voltages. My inverters do both voltages, 8,000 watts a piece. There's 5 of them. 3 of them hooked up to them, just bolted to the wall. No wires on them. Lightning hits, it's not going to get them from the wires. But you have your storage batteries. They're a constant nightmare of maintenance. The Tesla batteries are available. Tesla Powerwall is available. It's basically the battery bank from the car with no liquid cooling. The older ones were 18650 LiPo batteries, lithium polymer. That's 18 millimeter diameter, 56 millimeters long. The new ones are 2070, a little bit bigger diameter and a good bit longer in length. They use a different amount of phosphorus in the anode. Cheaper to build, more life cycles. Designed in conjunction with Tesla by Panasonic. They co-own a plant in a town called Sparks, Nevada, not far from Vegas. I got a buddy who works there. The headhunters found him in North Carolina. I met him in West Virginia, but they came to interview and took him out there. So I need to get up with him on some kind of a secure internet and find out what's going on. But Tesla makes a good power wall. If you want to make your own, you can make a better power wall. Cheapest batteries to buy because they're now going obsolete is 18650s. You get them used out of laptops and power tools like electric drills and cordless anything. That's the batteries inside of them. They may be several of them in series and groups of them in parallel, but that's what's in there. And one of them will be bad. You have to load test them. You charge them up and then you discharge them. See how long it takes to run them flat. And then you know good ones from bad ones. But you can buy them new. You want to buy authentic Panasonic or Sony or something like that from Japan. Try to stay away from overrated, unreliable data from the Chinese ones. Not that the Chinese can't build something. They definitely can build something. They do a good job on a lot of things. But their batteries just don't seem to be up to the advertised ratings. And when you go to hook them up, I use a spot welder. It's made just for that. But you want to fuse each battery. Every battery a fuse. And you say, oh, that sounds like money. It's not. They're 2 cents a piece, 2 cents to the battery. They're called glass fuses. If you have a maximum discharge rate before you have thermal runaway on a battery, you should never be drawn at more than half that. So you know what kind of a rating you want on your fuse. And it's 2 wires, well actually 1 wire goes across, and there's a glass sphere, a long thing, looks like a medicine capsule. There's a guy down there that used to work here. Maybe he's working here again. Anyway, the wire inside the glass bulb melts at a certain amps. And it's under a vacuum, you know. So it just disconnects the battery. If it's drawing too much charging, sending too much out discharging, the base of the battery is running across the glass fuse. Cheap to do. If you have one bad, you start losing capacity on that pack of cells, but they're easy to spot with a flashlight. You can change individual batteries. The other end is just a piece of electrical wire. The bus bar, it's nice to start them on a copper bar, but you can get a piece of number 4 or number 2, that's 02, not 2 aught, electrical wire, and take the insulation off and twist it. It's twisted already. If it isn't, you can twist it. And you can solder your stuff on that for bus bars. And to mount them, there's the reason for people using 18650s yet is there's a gray electrical conduit they sell at Home Depot and Lowe's in the U.S. It distinguishes it from the white colored plumbing conduit, PVC. It's thicker wall, but the batteries are almost a light press fit into that tubing. So you cut the tubes to the length you want, just a little longer than the battery, so you can have your connections up inside the tube. You stand them on end on a table, and you drizzle some PVC solvent cement down the cracks and glue them together. And then you just shove the batteries in, series and parallel. Series to boost voltage and parallel to boost the amp capacity. And you make groups of them, and then they connect you with bolts to another bar, top and bottom. You got a battery bank. And you got one that's safer than the ones that are bought because you're individually fused. Now on the anode end, that's the small connected end. You connect that up to a 25 cent voltage regulator. They're on a circuit board. Man, what's the size of that? 3.5 centimeters, maybe square. It connects to your twist wire or your bus bar unit. They connected to the system. On the other side, you've got 4 tabs, and you send one of them little wires to 4 different batteries. So for 25 cents, you can regulate the flow into 4 batteries. And so if you have 1,000 batteries in your battery bank, you need 250 of those 25 cent voltage regulators. And the wire you're going to mount it to your bus bar thing with, probably going to be about a number 12 anyway. And that's all you need for a mount. You can put a piece of plastic down to like pan do it or something and you know, screw them down. There's a bolt hole in the middle of them to screw them down if you want to. But basically all you need to do is electrical connections and it works. But your voltage regulator keeps it from drawing too much power when it's charging. If a cell is shorted out and it's drawn way too much, it's going to get hot. But before it has a chance to blow the fuse, the voltage regulator has already reduced the amount that it can get. So it can't get enough to get hot. And the fuse is then just a secondary backup. Well, video's too long again. So we're done today. Y'all have a nice day.